In the previous lecture, you explored artificial intelligence governance and regulatory compliance, where the enterprise must demonstrate responsibility, transparency, and measurable assurance. Now you are moving into the practical assurance engine that makes governance real. Artificial intelligence, red teaming, and adversarial testing. Governance tells you what you must achieve. Red teaming and adversarial testing show you whether you actually achieved it. In a world where artificial intelligence systems can be manipulated through language, data, and subtle inputs, you cannot rely on assumptions. You must test like an adversary. You must challenge your own systems before attackers do. In this session, you will learn how to think about adversarial machine learning attacks, large language model red teaming, and model robustness testing from an architecture perspective, not a hands-on configuration perspective. You will also understand where tools such as Pyrit, the International Business Machine's Adversarial Robustness Toolbox, and OpenAI Evolves fit into an enterprise assurance program. Before you explore specific attack categories, let us establish why red teaming has become unavoidable. Traditional security testing was designed for deterministic systems. You tested for known vulnerabilities, misconfigurations, and code flaws. You could patch issues and close tickets. Artificial intelligence systems are different. They are probabilistic. They are influenced by context. They may change behavior based on subtle prompt variations. They may degrade over time due to drift. They may respond differently when attackers apply psychological and linguistic manipulation. This means a secure configuration today does not guarantee safe behavior tomorrow. Red teaming is therefore not an event. It is a capability. It is the disciplined practice of continuously probing the system for failure modes, manipulation paths, and unexpected outcomes. For leaders and architects, this creates a new objective: build artificial intelligence systems that can be tested, monitored, and improved continuously. Now that you understand the need, let us clarify what makes adversarial testing distinct. Traditional testing asks, does the system work as intended? Adversarial testing asks, how can the system be forced to work against your intent? Traditional testing assumes cooperative input. Adversarial testing assumes hostile input. Traditional testing validates accuracy and performance. Adversarial testing validates safety, resilience, and integrity under attack. This distinction matters because many artificial intelligence failures occur when the system encounters adversarial inputs that were never considered in normal testing. As an architect, your goal is not to run tests yourself. Your goal is to design systems and assurance processes that anticipate adversarial behavior. Now that you understand the testing mindset, let us examine adversarial machine learning attacks. Adversarial machine learning attacks target the machine learning model through crafted inputs or manipulated data so that the model behaves incorrectly. These attacks can include evasion attacks, where inputs are modified in subtle ways to cause misclassification. Poisoning attacks, where training data is manipulated to embed harmful behavior or weaken detection accuracy. Inference attacks, where attackers attempt to extract sensitive information from model outputs. Extraction attacks, where attackers attempt to recreate the model behavior through repeated querying. As a leader, you should think of these attacks as threats to trust. If a fraud detection model can be evaded with carefully manipulated inputs, the business impact is immediate. If a medical prediction model is poisoned, safety outcomes may be affected. If a model leaks sensitive training data, privacy obligations are violated. Adversarial attacks undermine the reliability of artificial intelligence as a decision mechanism. Your security architecture must treat resilience as a design requirement, not a performance bonus. Now let us move into the area that is rapidly expanding in 2026. Large language model red teaming. Large language model red teaming focuses on the ways conversational systems can be manipulated to produce unsafe, unauthorized, or misleading outputs. This includes prompt injection attempts that override system instructions, jailbreaking attempts that bypass safety constraints, retrieval manipulation attempts that inject malicious knowledge, data exfiltration attempts where users try to extract restricted information through dialogue, tool misuse attempts where attackers coerce the model into executing dangerous actions. Unlike traditional security testing, large language model red teaming often involves social engineering style techniques. Attackers may phrase requests politely, indirectly, or progressively. They may use hypothetical scenarios. They may ask the model to roleplay. They may create multi-step chains to gradually erode guardrails. This makes large language model red teaming as much about psychology as it is about security. From an architecture perspective, you must design systems with layered controls and measurable guardrail effectiveness because attackers will probe boundaries continuously. Now that you understand adversarial threats, let us focus on robustness testing. Robustness testing examines how stable and resilient a model is under noisy, unexpected, or adversarial conditions. For a large language model system, robustness testing may examine how outputs change when prompts are slightly altered, whether safety constraints remain consistent across different phrasing, whether sensitive information leaks under pressure, whether retrieval results can be influenced through crafted queries, whether the system maintains reliability under load and repeated probing. For machine learning systems, robustness testing may examine sensitivity to small perturbations, stability under distribution shifts, resilience to adversarial examples, consistency across model versions. Robustness is a security property because instability can be exploited. If your model behaves safely only under ideal prompts, it is not secure. It is fragile. As a leader, you must demand robustness evidence as part of deployment readiness. Now that you understand what must be tested, let us consider how you design an enterprise program. Artificial intelligence red teaming cannot be a one-time workshop. It must be integrated into the lifecycle. A mature enterprise program includes defined risk tiers for artificial intelligence use cases, with higher risk systems receiving deeper testing. A library of adversarial test scenarios aligned to the threat landscape. Pre-deployment testing that blocks releases until minimum safety and robustness thresholds are met. Post-deployment monitoring with recurring adversarial testing. Incident response playbooks for artificial intelligence failures, such as data leakage or unsafe outputs. Reporting and dashboards that provide leaders with measurable assurance. This program becomes part of your governance operating model. It turns responsible artificial intelligence principles into measurable reality. Now that you have the program mindset, let us examine how specific tools support this discipline. Pirate is designed to help test large language model systems against adversarial prompts. It supports structured red teaming workflows that simulate prompt injection, jailbreak attempts, and manipulation strategies. It helps you build repeatable tests rather than relying on ad hoc experimentation. The International Business Machines Adversarial Robustness Toolbox provides capabilities for testing and defending machine learning models against adversarial attacks such as evasion and poisoning. It helps quantify model vulnerability and evaluate defensive techniques. OpenAI Evolves provides a structured evaluation framework for measuring model behavior, safety, and performance against defined test suites. It enables you to convert subjective expectations into measurable evaluation results. Remember, tools do not replace architecture. Tools support your assurance program, but your architecture defines what must be tested, what risks matter most, and what evidence is required before deployment. Now let us ground this in an enterprise scenario. Imagine your organization deploys a large language model assistant for customer service that can access customer account data and initiate service requests. You perform normal quality testing and the system performs well. However, during red teaming, you discover that a carefully phrased prompt can cause the system to reveal customer information beyond the authenticated user scope. You also discover that repeated probing can coax the assistant into revealing internal operational policies. This is a high-impact discovery. If you had not performed adversarial testing, the system would have gone live with a silent exposure risk. Red teaming turns unknown risk into known design action. It is not a blocker, it is an accelerator of safe deployment. Now that you understand the value, let us elevate this to executive assurance. Leaders do not need to know every attack technique in depth. They need measurable evidence that systems are resilient. This evidence can include red team scenario pass rates, safety constraint violation frequency, data leakage detection results, robustness stability matrix across prompt variations, model version comparison to detect regression. These metrics enable governance reporting. They also support regulatory readiness because you can demonstrate active risk management. In 2026 and beyond, the organizations that win will not be those who deploy artificial intelligence the fastest. They will be those who deploy artificial intelligence with measurable trust. Now that you have explored adversarial machine learning, large language model red teaming, robustness testing, and supporting tools, let us summarize the most important insights from this session. Artificial intelligence red teaming is essential because intelligent systems can be manipulated through context and adversarial input. Adversarial testing differs from traditional testing because it assumes hostile behavior and focuses on failure modes. Adversarial machine learning attacks target model behavior through evasion, poisoning, inference, and extraction techniques. Large language model red teaming focuses on prompt injection, jailbreaking, retrieval manipulation, data exfiltration, and tool misuse. Robustness testing measures stability under variation and adversarial conditions, and instability can be exploited. Enterprise programs must integrate red teaming into the lifecycle, not treat it as a one-time event. Tools such as Pirate, the International Business Machine's Adversarial Robustness Toolbox, and OpenAI Evolve support repeatable testing and measurable assurance. Measurable assurance enables governance, regulatory readiness, and safe acceleration. Now that you understand why artificial intelligence, red teaming, and adversarial testing are essential for trustworthy deployment, reflect on your organization's current posture. Are your artificial intelligence systems being tested adversarially or only validated for normal behavior? Do you have repeatable test suites or one-time demonstrations? Do leaders receive measurable assurance or informal confidence? If this lecture helped you strengthen your enterprise architecture mindset, subscribe to the channel so you do not miss the next session. Like this video if you believe that testing like an adversary is essential for responsible artificial intelligence adoption. And comment below with your perspective. Does your organization have a structured artificial intelligence red teaming program? Or is deployment still moving faster than assurance? Let us build secure, resilient, and trustworthy artificial intelligence systems together.